Okay, so good afternoon. Um, Before I start, I would like to make a couple of announcements which I sort of forgot yesterday during my talk. First of all, I would like to thank the organizers, I guess Rajiv and Amita, for giving me this opportunity to present some of my work on laser plasma acceleration. I presented a talk on positrons yesterday. Today I'll be speaking about electron acceleration. And the second thing I want to sort of note is that all of this work is being done at the Department of Physics and John Adams Institute at the Imperial College London. And I think there was a plenary talk which summarized a lot of the a lot more of the work that is being carried out by Professor Najmuddin, who was there earlier. So most of this work that I've been presenting is in the domain of sort of doing simulation and theory for while interfacing with the group and obviously coming up with new ideas and trying to explore new physics of laser plasma acceleration and laser plasma interactions in general. So today I'll be presenting some work on laser plasma electron acceleration in what is being termed as a strongly mismatched regime. And I'll explain you shortly why I'm calling that a strongly mismatched regime. Even before we jump into the whole details of the laser plasma interaction that drives the acceleration process, we can take a snapshot of what we are talking about. So in this picture, you're seeing a laser pulse which is at the head this is a PIC simulation snapshot, and you're seeing a laser pulse which is at the head, which is basically propagating in the plasma. And because of its Ponderomotive force, it's driving this blowout of electrons such that a region of the plasma is evacuated. And by doing so, the laser pulse is able to create, self-create or self-excite a plasma density gradient, which acts as an optical fiber to keep the laser pulse guided. So what I'm getting to is that we are in the self-guided regime of the laser pulse. If you think about a focused laser pulse, the laser pulse would tend to diffract away once it's focused. Right after it's focused, to start diffracting, and it's typically parameterized by what is called as the Rayleigh length of the laser. And in our work, Rayleigh lengths are of the order of few millimeters. But what I'm going to be showing you is electron acceleration results over several tens of millimeters, so 20 millimeters or 25 millimeters. So getting back to the basics, I think this work is all in the self-guided regime. And typically in the self-guided regime, you go into a cavitation mode, which drives a nonlinear plasma wave, which is in the blowout regime. The nonlinear plasma wave is in the blowout, as you can see here. And the unique aspect of this work is that the bubbles that are typically excited, that are well known and well understood, are spherical bubbles, and we'll see why we get to this sort of elongated bubble, longitudinally elongated bubble in this case, and what significance it has to our work. Okay, so just a brief outline. We are looking at high energy electron acceleration, multi-GeV, using a self-guided laser pulse. You're not using an externally guiding geometry, which several people use, for instance, using capillaries or discharges. So this conventional understanding is that there is a matched regime of this laser plasma interaction, and that matched regime is assumed to be optimum for accelerating the electron beams to highest energy. And the reason is that because the structure of the matched regime, the structure of the plasma wave is much stable, which basically implies that the radial dimensions and the longitudinal dimensions of the plasma wave are relatively stable over the propagation of the laser pulse, and thus you are able to continuously interact with a certain phase of the plasma wave as a beam. As a beam basically interacts with a constant phase, so you can continuously gain energy. But what we are looking at here is we are looking at a mismatched regime, and we're trying to see if we can get to high energy, high quality, high efficiency electron beam production using the mismatched regime. So automatically, one of the questions that might arise is, why are you looking at the mismatched regime? And I'll to why mismatched regime may be attractive from certain considerations as opposed to the matched regime. Okay, and then I'll be showing you that you can get such very high quality, high energy beams. We'll be explaining the production of those beams using the adjusted A0 model. And I'll be showing you that this process of the mismatch regime only is optimized over a certain narrow plasma density range, and that corresponds to where an optical shock is excited. And we'll explain all of this relatively complex laser plasma interaction by looking at the evolution of both the laser plasma properties and also look at the beam before I summarize. So what are we talking about here? The matched regime, which is sort of a well-known regime for laser plasma community, is a regime where the laser Ponderomotive force is balanced by the nonlinear plasma response. So if you go back to the picture of the bubble, the laser pulse is driving a cavitation regime. So cavitation regime is where the electrons are basically blown out from the path of the laser pulse, and there is an ion cavity which is left behind. And this ion cavity basically has an electrostatic pull on the electrons that are blown out. So if you balance the Ponderomotive force that is acting on the electrons that are being blown out to the electrostatic force of the ions on those electrons, you can you can artificially induce an equilibrium so that the laser pulse doesn't oscillate radially. So this is what is called as the matched regime, and it's well known that if you initialize your laser pulse with a spot size, which follows this relation, then you can keep the laser pulse envelope relatively stable. And if you keep the laser pulse envelope relatively stable, then you can keep your plasma wave dimensions relatively stable as you guide and accelerate the electron beam. And in this matched regime, based on some very interesting work by Professor Mori's group at UCLA, this famous paper by Wei Lu et al. Tells you that the energy gain in this matched regime goes as 2/3 A0 times N critical over N0. And I'm assuming you all know what N critical is, so I won't go over that. But basically, this is a 3D simulation, 3D PIC simulation based scaling law, which many people compare against. So let's look at what is the context in which we are investigating this work. So there have been several experiments at Gemini on self-guided laser regime for electron acceleration. One such result is presented in this paper by Stefan Nee et al. In 2009, where they showed that you could actually get to close to 1 GeV electron beam by using a plasma with a density of 5.5 10 to the 18th per centimeter cubed, and a typical Gemini laser pulse of 10 joules and A0 3.9. So if you go to the equation for the energy gain in the matched regime, it only predicts energies which are 510 MeV high. Whereas in the experiment, you get to energies which are 800 MeV, as high as 800 MeV on some shots. Then we went back in August 2015, and we used what is called as the F40 imaging optics, which is sort of the numerical aperture of the final focusing off-axis parabola, which takes the collimated laser beam to its focal spot. And what we see is that with this type of, with this focal spot of the laser pulse, we get to energies which are of the order of 2.2 GeV. Whereas the equation only predicts energies which are less than a GeV. So there is a big degree of mismatch between the predictions of the matched regime scaling laws and the results that we are getting in the experiment. But I'm not referring to this mismatch. This is just the mismatch between the predictions and the energy. I'll show you the strong mismatch that I'm talking about in the next slide. So if you look at the August 2015 F40 data, the wave sizes of the laser pulses are, 37.4. It's an elliptical focal spot. So one of the axis has it's the semi-minor axis, if you want to call it, is 37.4, and the semi-major axis is 44.2 microns. And you can work out with that type of power levels, that sort of energy level, you can get to an A0 of 1.9. Again, I'm assuming you all know what A0 is, so I'm not talking more about that. So the strong mismatch that we have in this situation is that the match spot size for these parameters with F40 optics are that you have with the given A0 that you have a W0 of 10.3 microns, but we are actually in experiments launching the semi-minor axis, the smallest focal spot dimension, sort of 37.4. So it's an order of 4 mismatch between the match spot and the experimental laser focal spot that is incident on the plasma. Similarly, in the F20 experiments, which is basically the 2009 result, At 5.5 10 to the 18th with A0 of 3.9, the match spot size in that case is 8.95 microns, but they were launching at that point a focal spot that was 19 microns. So again, this is exactly the mismatch I'm talking about. So there is a strong mismatch between the radial envelope of the laser pulse and the nonlinear plasma response. So the two basically are mismatched. And as you can imagine, if we are not forcing an equilibrium from the initial conditions, the whole interaction is not very stable. And that's why earlier I had referred to this being complex laser plasma interaction. So what we have done is we have to explain these energy data, we have used what we are calling as an adjusted A0 model. And in this model, what we are assuming is that the laser pulse, all the energy that is incident in a laser pulse envelope is basically being squeezed down to the match spot size. And if for those of you who know the relation between the numerical aperture and the F number of the pulse, you can see that the pi W0 over lambda 0 is sort of the F number. So we can write a relation which is experimentally valid for a larger F number of the final focusing parabola. And using this adjusted A0 model, we see that we are able to explain energies which are as high as 2.2, even though the equation predicts only less than energies 1.0 JeV. And in 2008 data, we see that we are able to predict energies as high as 957 MeV, whereas the equation 2 only predicts 510 MeV. Then this slight mismatch may be because the pulse energy at that time was not exactly 10 joules. It was probably 8.5 joules, but that's a minor correction. So what we are saying basically is that using an adjusted A0 model, where the A0 is bumped up by taking into the consideration the squeezing of the laser envelope to the match spot size, which can be represented this way simply, A0 launched divided times the W0 launched over W0 matched. That's the adjustment in A0. So with that, we are able to see there is a much better match between the electron energies. And then if you basically plot the results of equation 2, we see that with 10 joules, at sort of 10 to the 18th, you would expect 0.6 GeV, which is 600 MeV beam. But with the adjusted A0 model, you're able to get to 2.2 JeV in this case. So this is just a plot to show you that we have taken the A0, which is originally 1.9, and the adjusted A0 works out to 7.4. So that basically explains. But there is something more interesting, which is that this adjusted A0 model, or even equation 2 or the original match spot size based energy gain model, doesn't predict the experimental signature, which is that there is an optimum density range over which this model predicts correctly. So both the model based on Wei Lu's paper and the adjusted A0 model predict the high energy beams only over a certain range of densities, which is appearing both in 2008 data and 2015 data. So in 2008 data, this is the 800 MeV shot, but if you look at the sort of the trend, the highest energies are only obtained over a range of between 5 and 8, 10 to the 18th, and then energies basically drop off really fast for densities which are lesser than 5.5 and for densities which are greater than 8 or so. And a similar effect actually happens in 2015 F40 data as well. Going to lower densities doesn't always bump up the energy, even though you can see there are trends which show that if you go to lower densities, you can actually bump up the energy. You can see that there are at 1.8 10 to the 18th, the beam is close to 1 JeV, whereas for 3.2 or even 2.8 or even 2.4, you can see that the beams are much higher energy, reaching greater than 2 JeV. And if you look at the data beyond 3.2, obviously it again trails off. So there is some explanation due for why this happens. And that explanation can be only done through looking at the complex interaction dynamics that's going on when we launch an initially mismatched focal spot size. And if you look at why the adjusted A0 model is valid, it's very easy to observe this fact that the plasma takes in the pulse, which is launched with the FWHM spot size of 44 microns and squeezes it close to the match spot size of roughly 10 microns. And on average, the focal spot W0 remains close to the match spot size. So during the acceleration process, the A0 is bumped up, or the energy is basically being squeezed to all close to the match spot size. But the more interesting aspects are that if you look at, so that's why the adjusted A0 model is valid. And if you look at the laser pulse temporal envelope, you see that you start with the pulse, which is about 35 femtoseconds long. And as the interaction happens, there are these events where the laser pulse is basically undergoing this catastrophic events. It seems to be undergoing these catastrophic events where the laser pulse temporal FWHM, the time FWHM of the pulse basically drops to very low value, then it again builds up, again drops to a very low value, and then these events happen regularly. And I would also like to mention that the in figure B, we have plotted the laser field and the plasma field. And what you can see is that these behaviors are basically both correlated. So as the laser field rises at close to a squeeze event, this is the laser waste undergoing a squeeze event, the laser field rises, and soon after there is this catastrophic event. And similarly for this surge in the laser electric field, there is a corresponding catastrophic event, and corresponding to this increase or surge in the laser electric field, there is a catastrophic event. So these catastrophic events seem to be happening in correlation with the surge in the laser electric field. In addition to that, the black curve here shows you the length of the bubble. So you can see that the bubble length actually is much bigger than the radial size of the laser pulse, or radial size of the bubble. So this is an asymmetric or elongated bubble. And corresponding to that, we're seeing that the plasma field actually has these dips corresponding to these catastrophic events. So when there is a catastrophic drop in the laser pulse length, the plasma field actually rises. And that can be sort of explained by looking at the disbalance between the longitudinal Ponderomotive force and the radial Ponderomotive force. And the fact that we'll show you shortly that each of these catastrophic event actually is an optical shock state. So the laser pulse is entering what is called as an optical shock. So what is the optical shock? I'm plotting one such event around 24 picoseconds to show you why there is a huge drop in the laser time FWHM. And you can see that initially the laser pulse drives this density bump in the front of the wake. So this is the front of the bubble. And as the laser pulse undergoes squeeze in the radial direction, the laser pulse amplitude rises, and thus the Ponderomotive force that is driving this front of the wake is also rising at the same time. So there is a local increase in the density in the front of the bubble. And then you can see at a later time that is basically slicing the laser pulse into two parts. And this is the optical shock state. So Ponderomotive force basically is the gradient of the laser pulse envelope. And you can see that here the gradient of the envelope is almost infinite in some sense. But let's try to understand why this optical shock is excited. So if you go to the third order perturbed group velocity of the laser pulse in these interactions, you see that is related to the group velocity in unperturbed plasma, but it has these terms. This is the A value of the envelope, so that's the averaged squared, and the perturbed density normalized to the plasma density. You can use this relation to derive a condition where you would have the zero local group velocity. So okay, before even we jump to that, this relation tells you that each cycle of the laser pulse has a different group velocity depending upon where it is relative to the plasma. So if you ignore this A0 squared, assuming A0 squared is a minor effect, delta n over n, where delta n over n is maximum, the group velocity is minimum, sort of. So based on that, you can derive a zero local group velocity condition. So if the delta n over n minus a squared is of the order of nc or n0, the group velocity will be zero. Group velocity zero means basically phase velocity being infinite. So that implies a wavelength elongation. So you can see that what happens here is that as the density buildup starts increasing due to a squeeze of the radial envelope, the photons which are in this region or the cycles of the laser pulse, depending upon which picture you like to see, they are undergoing a reduction in the group velocity. So their wavelengths are basically increasing. So that's basically a redshift. So this increase in the local increase in the wavelength is slicing the laser pulse in two. So there is a small slice which is in the front, and there is a slice which is driving the wake, which is sort of in an optical shock state. So this local group velocity difference is what is basically leading to this optical shock excitation. And then what we have done is, based on simulations, we have plotted the value of the Ponderomotive force. And you can see that each time there is a squeeze event, the blue curve shows you the longitudinal Ponderomotive force. The longitudinal Ponderomotive force undergoes a big increase at that time. So this specific increase in the longitudinal Ponderomotive force corresponds to one of the biggest elongations of the bubbles, because there is a big disbalance between the Ponderomotive force. The longitudinal Ponderomotive force is much bigger than the radial Ponderomotive force. You're driving an elongated bubble, which is doing two things, which is first exciting. If you go back to this picture, you're seeing that the bubble length is basically increasing. The blue curve is the electric field of the back of the bubble. And you're seeing the back of the bubble in this at 25 picosecond has moved all the way much further back from the laser pulse. So basically the bubble is elongated. So this elongation is basically also injecting a charge. It is leading to much higher electric field because much more ions are evacuated. So using Poisson equation, you can easily see that there's a much higher electric field there. And thirdly, because of the lengthening of the bubble, the dephasing length has also increased. So the electron can gain energy for a much longer distance before the electric field goes to zero and then goes to positive, which is decelerating for the electric fields for the electrons. So electrons can ride for much longer in the wave in the elongated bubble. So this is sort of the complicated dynamics of the laser plasma interaction. And now let's quickly take a look at the properties of the electron beam that we observe in the simulations as well as the experiments. The first thing that I would like to point out here is what I'm plotting here is the peak electron Lorentz factor. So that is just the maximum Lorentz factor of the electron in these simulations. Okay, so as most of you know, the beams that are accelerated using laser plasma accelerators are not ideal beams, in the sense that they don't have a monoenergetic spectrum. And they have a large energy, obviously, which implies that they have a large energy spread. So in this simulation, in this plot, I'm just plotting the highest Lorentz factor amongst all the particles. Okay, so one feature which is very clear from this plot is that by scanning over densities, we see that there is an optimum density where you get the highest energy electron beams. And in this case, that corresponds to something like 2.0 and 2.2. So this is a rough match to the experimental signature that we have. So the orange curve is 2.2, the red curve is 2.0, and in both these cases, we see that we get beam energies which are in excess of 2.5 GeV over a distance of 66 picoseconds would correspond to 20 millimeters or 2 centimeters. So this is again matching sort of what we see in our experiments. We get to beams of 2.2, 2.3 GeV over 20 millimeters. Whereas if you look at 1.5 10 to the 18th, you see that you get a highest energy of 1.75, for example. With 3.0, again, you get highest energies which are of the order of the 1.75 GeV. So what this is telling you is that the complex interaction dynamics limits the optimum density range for maximum gain of energy of the electron beam to a certain optimum, within a certain optimum density that we should shoot for, based on all the complex dynamics that we saw earlier. And the other thing we see is that there seem to be two different slopes to this curve. So initially, the laser, the beam that is having the peak energy seems to come and sort of trail off around 2000, which is roughly 1.25 GeV. And then there seems to be a secondary injection at around 24 picoseconds, which is where the optical shock is formed. And that beam rapidly accelerates off to 2.5 or 2.25 GeV, for example, in this case. So, and this is what we are seeing both in experiments and in theory, that there are two major injection events corresponding to two of these optical shock formations. And before I summarize, I would like to show you the nice high quality bunch that are injected by this optical shock state or the elongation of the bubble. And the way I have qualified these properties, I'm still working with the experimentalists to see if they get similar properties in the experiments, because they haven't been able to fully qualify the emittance of the beam yet. But from simulations, it's relatively not that hard to actually find out the properties. And in my simulations, I'm seeing that the RMS transverse size of the highest energy bunch, on the top, you're seeing the RMS size of the highest energy, meaning the energies which are within 90% of the gamma peak. You see that they, towards the end, which is where they are 2 GeV, they are sort of, close to 100 nanometer scale beamlets in transverse RMS size. So that's pretty tiny for a transverse size. And the other thing that we have, investigated is the angular spread of this bunch, and even that one we see is, around 100 microradians. So that gives me a geometric emittance which is 10 to minus 5 millimeter milliradian, which is normalized, which gives me a normalized emittance of 0.1 milliradian, which is, it's a very unique, sort of very nice beam quality. Anything below 1 millimeter milliradian is considered to be very high beam quality. And we are able to, trace this back to the excitation of the optical shock and the elongation of the bubble. So most of the electrons are injected very close to the axis, so they don't have too much transverse momentum to start with. And that's why the focusing force on axis is 0. So they don't see much focusing force of the bubble. But there are some possibilities of big mismatch between simulations and experiments, because it's well known that as the beam exits the plasma, it undergoes this plasma ramp at the exit of the plasma stage, and this can cause some emittance reduction due to various factors. So let me quickly summarize. I'm running out of time. The match spot size, going back to the question that we sort of brought up earlier, is why having a match spot size may not always be the most optimum, and the answer doesn't lie in theory. I personally think that it doesn't lie in theory or in simulations. It lies more in the experiments, because in experiment it's harder to achieve a perfectly nice looking Gaussian focal spot when you are 10 micron when you're trying to achieve a 10 micron waist size, whereas it's much easier to achieve a uniform spot size when you're going to 40 micron or 37 micron in this case. So that probably is one of the reasons that you can you get to much higher energies. It's well known that plasma wave transverse profile gets distorted if the laser profile has some hotspots and non-uniformities, and having distorted transverse profile is not very good for sustained acceleration. So this basically tells you that if you get a perfect Gaussian spot with a matched spot size, you might be able to get to even higher energies as compared to a mismatch regime. But in this case, because of the experimental considerations, we see that the strongly mismatched regime is able to give you peak energies which are sort of greater than 2 GeV, which is explained using an optical shock excitation, which is based on slicing up of the laser pulse due to its envelope dynamics. And we see that the elongated bubble gives you much higher peak fields of the order of teravolts per meter in the plasma, which is very high for the plasma, and you get much longer dephasing lengths. And finally, the injection schemes that we automatically get driven by these elongating bubbles lead to very high quality bunches, where you can possibly achieve emittance values of less than 1 millimeter milliradian, which is pretty good. And one last point before I conclude is that you can get much higher total efficiency, because in the matched regime, you don't inject as much charge because you're not undergoing any of these asymmetries in the problem. So you don't inject as much charge as compared to the mismatched regime, where you by design being in a non-equilibrated stage, you inject much more charge. Note, not all of this charge is coupling to the highest energy beam, but there is charge at even lower energies, basically. So that if you count the total energy in the bunch that is coming out of the plasma, the laser energy to total bunch energy, efficiency is much higher. So thanks a lot. Any questions, please?
Aakash. Yes.
You are getting mismatch between the bubble radius and the laser spot size. This is, can you explain why? And is it a function of time? Is it oscillating?
Yes.
Bubble
Okay,
phase is oscillating?
Yes, exactly. So sorry, I was running too fast, Professor Tripathi. Sorry for that. Just give me one moment. I'll show you. Okay, so if you look at this curve in A, this is plotting three properties. Okay, so the blue curve is showing you the radial envelope of the laser pulse. This is based on FWHM. Okay, this is based on calculating the FWHM of the laser pulse. So you see that initially when you launch a really big spot size of the laser, it squeezes down to close to what the match spot size is, and then it keeps oscillating. Okay, so the blue curve here is pointing to the wave size of the laser pulse, which is also equal to the radial size of the bubble. The black is the bubble length, is the length of the bubble. So that's, considering from the start of the bubble to the end of the bubble longitudinally on axis, for example. That is elongating much more than radially expanding. So this bubble is asymmetric. It's an elongated bubble. Interestingly, you see that each time the laser pulse undergoes a compression, its electric field undergoes these surges, right? So if you look at this compression event, the first compression event, the laser pulse electric field is going up to a very high value of 30 teravolts per meter. Then there is the second compression event right here, corresponding to which the electric field again goes up, and then there is a compression event here. The electric field again goes up. So you're right. That's exactly the whole point, that because of this initial radial mismatch, strong radial mismatch, the laser pulse radial envelope keeps oscillating. But on average, it remains quite close to the match spot size, as you can see here.
Wonderful, wonderful, very nice. Thank you.
Thank you.
Thank you. Wonderful.
Yeah, thanks.
Any other comment or questions? Yeah. Second.
Yeah, it is continuation of only that mismatched region. But how does it lead to higher energy? I mean, basically you are scaling A0 to the higher level by considering the radius equal to the bubble dimensions. But it would take certain length also to match to the bubble radius. So
Yeah. So actually, if I
it
go
may not
back,
necessarily lead to the higher energy. I mean, because you have to take into account the length already taken into account for coming to that matching condition again.
yes, that's correct. So the most interesting aspect is that if you look at, just to give you some numbers, at 210 to the 18th, the wave breaking field is of the order of 136 gigavolts per meter. Okay, take my word. And if you look at the peak electric field in the plasma corresponding to one of these shock events, so if you look at the shock event, the optical shock event at 20 picoseconds, where the time FWHM collapses to a very low value, around 20 femtoseconds. In this shock event, the peak plasma field is roughly 800 gigavolts per meter. So it is roughly 7 times its wave breaking value. Okay, so if you think about, let's assume that is not 800, but that's 1 teravolts per meter. In 1 teravolts per meter, if you want to go to 2 GeV, that is only 2 millimeters, right? Okay. So the whole dynamics, the whole point of a sustained acceleration, the whole picture of thinking about a matched regime doesn't apply here, because the peak fields are crazy big, right? So the peak fields, if the peak fields are so high, then you don't need the acceleration length. So the whole intuition based on matched regime is sort of thrown out basically.
So you are saying that basically due to high electric field is still available, the length is sufficient to provide higher energy.
That's right. Yes.
So, but you are compromising on the beam quality, as you already mentioned that there could be multiple injections and there could be some quality compromise.
Yes, definitely. The energy spectrum is not ideal. In matched regime, you would get if you get one injection, if you can control your dynamics to get one injection, then you would probably get one beam which has a controlled energy spread. But because there are multiple injection events, you get beams of many different energies. but the transverse qualities are pretty good because of this elongated beam injection, which is very similar to down ramp. For those of you who know the down ramp injection, this injection is very similar to the down ramp injection, and in down ramp injection you get very nice transverse qualities of the beam. So the transverse properties are very good, but the energy spectrum is not very nice. But you can use post processing, like sending this beam through a spectrometer and only filtering out a certain energy of the beam if you wanted a very nice energy, a very nice beam.
Thank you.
Yeah, you're welcome.
Okay, so let's thanks to the speaker again, and